Alright, today we're going to get started on covalent bonding, which is kind of the opposite of ionic bonding. They do have similarities in that they are forming bonds to follow the octet rule, but remember, ionic bonds occur between metals and nonmetals as they transfer or kind of give and take electrons, forming ions. Covalent bonding occurs through the sharing of electrons, and we are going to represent these through lines, kind of a line and dot structure. We're going to call them Lewis structures again, but it's kind of a different process of drawing this molecule using the valence electrons because they're shared. It's not a complete and perfect transfer like in the ionic compounds, and they're going to be shared through bonds that connect atoms. Additionally, covalent bonds occur between nonmetals only, so there's no metals involved here. So let's start by talking about their key properties. We just said that they follow the octet rule by sharing electrons. They share electrons through bonds. Sometimes there are multiple bonds, so we will talk about that when we look at shared pairs or single bonds, double bonds, and triple bonds, but all of those are sharing electrons. Covalent compounds are made of nonmetals only. And then in terms of like their compound properties, they have generally low melting points and boiling points, and weak or poor conductors, and insoluble or weakly soluble. We'll generally say kind of they're insoluble. Those are key properties of covalent compounds. Whenever we're talking about a covalent compound, another term that can be used to describe these type of compounds is molecule, and we are going to draw Lewis structures of molecules. So a molecule is just another name for covalent compound. Any total nonmetal compound is considered a molecule. And when drawing molecules, we need to follow two rules that will be important. And those two rules are to first count the valence electrons and use exactly the sum of the valence electrons in the molecule. So you will find all of the atoms that are participating in the covalent compound, add up their valence electrons, and then you will use them to share to complete the octet. That's our second rule. Complete the octet using lone pairs. And we'll talk about what shared pairs and lone pairs are here in a moment. So you count the valence electrons and use that many, and then complete the octet using lone pairs. This will be a little bit more concrete in a minute when we do some examples, but let's continue discussing covalent compounds before we go to our example to actually draw these. So diatomic elements, we have talked about these before. Diatomic elements are molecules that are formed from two identical atoms. I kind of talked about them as sort of twin molecules. And so there are 7 that exist in nature, formed from identical atoms. And it's always 2. Di means 2. So diatomic, molecule formed from 2 identical atoms. There are 7. And we are going to memorize these. We've listed them before, but now we're going to kind of get a little bit more serious about memorizing these. It will come in handy when we do naming and when we work on reactions in next semester. So our 7 diatomic elements are hydrogen. I'm just going to write their chemical formulas. Remember, a little 2 is telling us how many, so there's 2 hydrogens bonded together. So that's hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Those are the 7. Hofbrinkel. That helps you remember. Silly words sometimes make things stick. Hofbrinkel. Those are our 7 diatomic elements. Now about our electrons within our molecule drawings. We have 2 different pairs of electrons, or ways that electrons are drawn. So we have shared pairs, which is a bond of shared electrons between connected atoms. So a shared pair contributes all the shared electrons to both atoms that they connect. So when we have a single bond represents 2 shared electrons. That means both atoms that are connected by the single bond gets 2 electrons from that bond. So in a way, it's kind of contributing 4, 2 to each atom, although it represents just as 2 when you count the valence electrons. It is shown just as a single line connecting the 2 atoms. A double bond is going to be a double line, almost like an equal sign connecting the atoms. Each line is 2 electrons being shared, so this would be 4 electrons. And then a triple bond is 3 lines connecting, and this one would be 6 electrons shared. The other way that you can express electrons in a Lewis structure for covalent compounds is through a lone pair. And a lone pair is made of electron dots that represent unbonded electrons. And they're written in pairs, so if you see 2 dots together, that's a lone pair. You'll see that, and they only belong exclusively to the atom that they're written beside. So we can make a note here. They belong exclusively to the atom they are written beside. So these are not really shared between multiple atoms, but they do come from kind of a shared pool of valence electrons when drawing. One more note about these bonds of single, double, and triple bonds. Bond strength grows with the number of electrons shared, so you'll see our triple bond is going to be the strongest and our single bond is the weakest, and the stronger the bond, the shorter it becomes. So our triple bond will be the shortest, kind of like that stronger pull idea makes it shorter, and then our single bond will be longer. So we are going to practice now drawing covalent compounds. We're going to do a couple on this video, and then we will do a part 2 to kind of complete these examples. So let's start together following our 2 rules, which are written here again. Count and share exactly the molecules' sum of valence electrons, and then complete the octet for every molecule. So those are the 2 rules. Get the valence electrons exactly from the sum of what our atoms contribute, and then complete the octet. So what we mean by this, we're going to share with multiple bonds if the diagram exceeds the available electrons. And when sharing, if we have a polyatomic ion, a negative charge means add extra electrons, and a positive charge tells us to take away or have deficient electrons from when it's neutral. And we will complete the octet using lone pairs. And here we have listed the different octets. Remember that hydrogen is stable with 2 and all else are stable with 8. There's one other kind of exception to this octet rule for covalent. Boron is content with 6. So that's just another little rule, kind of funny, but boron is okay with just having 6 valence electrons. So let's do an example of this with bromine, Br2. First, we want to count and share exactly the molecule's sum of valence electrons. What we mean by this is that each bromine, if you remember when we were drawing Lewis structures, each bromine brings 7 electrons to the table, right? And so in our ionic compounds, we would transfer these, but you'll notice both of these need to kind of gain an electron, right? And we'll notice that on all of these because they're all nonmetals. So transfer is not going to work anymore. That's why these are a different type of bonds. So what we're going to do is pool all of our electrons together and share them so that they do have a complete octet. And what will happen is these two kind of alone electrons, I'm going to circle them, they will end up being shared in between the bromines and form a shared pair. Okay, so together our bromines end up having 14 because 7 from each is 14 available valence electrons. That's our molecule sum. So we counted them. Now we need to share that amount. So the way that you will set up your drawing is you'll put all of the atoms in the molecule around each other. If it's just 2, they'll be in a line. But then after 2, you'll kind of start to put them in some sort of formation like so. Kind of like an X or T will be the general formation that you put them in. And then we surround them with lone pairs to finish our octets. So right now we're sharing 2 in the middle. That means that, let's start with our left side bromine. If it is sharing 2 to complete its octet, doing this second step, we need to put lone pairs around it to reach 8. So it's going to be 3 lone pairs, 2, 4, 6, and then our shared 2 in the middle. And the same will apply for our bromine on the outside, on the right. So each one has 3 lone pairs and then a shared pair in the middle, completing both of their octets because of those shared electrons in the center. So there would be our completed and following both of our rules Lewis structure. We'll do NH3 also on this one, and then we'll do part 2 for carbon dioxide and phosphate. So nitrogen with 3 hydrogens. Again, let's just kind of count our electrons by drawing individual Lewis structures here to the side. I have 1 nitrogen and 3 hydrogens. So that will be a total of 8 electrons to share. Let's go ahead and draw this. And if you kind of think about it again, these spots are open for our nitrogen, and our little hydrogen guys are going to end up kind of sharing over in the lone spots of those electrons. So the way we'll set this up, put nitrogen in the middle. Usually when we're drawing these, put the different one in the middle. You'll have like, you'll see PO4, put P in the middle because it's a different element. And then surround it with the elements and connect. Okay. Now we're going to complete our octets. So remember that every hydrogen is stable with 2, so they're actually already stable with these shared bonds. They don't need any lone pairs. However, nitrogen currently is, it has 2 from this shared bond, 2 from this shared bond, and 2 from this shared bond, which makes 6. It needs 8 to be stable, so it needs a lone pair added here. We have counted them all, and we've completed our octets. Let's make sure that we're using just these 8. 2 from this bond, 2 in this bond, 2 in this bond, and a lone pair. That's 8 electrons being used. So we did correctly use our valence electrons. If we go back to bromine and do the same check to make sure we used only these 14, we have 2 in this lone pair, 4, 6, 8, 10, 12 in all of our lone pairs, and then 2 in a shared pair, so that is 14. Also used them. That's going back to our first rule, count and share exactly the molecule sum. We were just checking that we used exactly the molecule's sum. Come back to part 2 for CO2 and PO4.